This is example 3 from lecture 1, part 1. Here we're doing a dimensional analysis with a pendulum as an example. Okay. So the question reads that the period of a simple pendulum is the time it takes to make a complete oscillation or a swing. Assume that the potential physical variables that can affect the period are gravity, the pendulum length, the mass of the bob, and the angular deflection, which has no dimensions because it's measured in radians. It could also be measured in degrees. Using dimensional analysis, what does this tell us about the period as a function of these properties? So without knowing anything about particular theories related to pendulums, or even to motion under the influence of gravity, we could just use our knowledge of physical dimensions, because every equation in physics is only true if both sides of the equation are both numerically equal and dimensionally equal. Okay, so we are told that the period t is a function of theta. And I'll put these in the order that they're presented. So the first one was gravity, so that will be represented by a g. The length, L. The mass of the bob, m. And theta. Okay? So notice that here I'm using the variables, not the dimensions. Okay, so that's our variable for period. Okay, we also have this here is gravity. Okay, length and mass are shown in the figure, as is theta, which is the initial deflection. Okay, so we're proposing that the period can be a function of all those. It need not be a function of all of them, and that's what we're going to find out. Okay, so we're going to set this up in terms of dimensions now. So period is a measure of time, so it has dimensions t. Coincidentally, it's the same uppercase letter. Okay, so that's one side of the equation. The other side of the equation, we're going to put the dimensions of all the different variables. Okay, now we're going to have them multiplied together, but we also don't know the power that they are raised to. Okay, so here we have the dimensions of g. Now it turns out that the dimensions of gravitational acceleration are L over t squared, which is specified in the problem above. All right, we're told that gravity has dimensions of length over time squared. Okay, so that's going to be raised to some power. I'm going to use A, B, and C, and so on to represent the variables that we're solving for, which are the powers of the different dimensions. Okay, and then this is going to be multiplied by the length to some power B. And then we have the mass, uppercase m, because the variable was lowercase m, but the dimension is uppercase. That will be c. And since theta doesn't have any dimensions, it will not be included in the dimensional analysis. So what we have here is that there's no effect from theta, so not included because no dimensions. And I'll get back to the consequence of that in just a moment. Okay, so we'll continue on. So what we have here is we have this equation with all the different dimensions represented in brackets and raised to different powers. But how do we solve it? Well, we set it up as a system of equations. So what we have really is we have t on the left-hand side of the equation is raised to the first power, because we know that period is in fact time. It's not the inverse of time, it's not time squared, it's just time. Okay? So that tells us that then we can go through and we can find out, you know, how these other variables are related to time. Okay? So what the system of equations would look like by considering the exponents, we'd have 1, all right, is going to equal, okay, negative 2a. All right? Any other times? No. Okay? So how did I get that? Well, If you think about it, we have here, we have notice, we have the 2 is the power of time in the denominator. So we could express that exponentially as a -2. And then when we have the exponent a outside of the brackets, we would multiply those exponents together. So the -2 multiplied by the a becomes -2a. And so we know that dimensionally, if there's a power of 1 on the left-hand side, they must be equal to the -2a on the right-hand side. Okay. Let's get this back into frame. All right. Okay. So what we then want to do is continue on. So we want to do the same things for B and C. And both sides of B and C, well, let's see what we get, right? Well, we know we're going to have 0 over here, okay? And then what do we have? And this is, and here I'm just going to consider, so really I guess what I'm considering here is each dimension, okay? So this one I'm going to take a look at L. So there's 0 L's on the left-hand side, but on the right-hand side I have a plus a b. So a plus b must equal 0. So just to label where these equations are coming from, we can call this the t equation, right? Paying attention to matching up all the time dimensions on the left and right hand side of the equation. Here, this is for length, and then the last one will be for mass. Okay. All right, so let's do the one for mass now, since we've finished with length. Well, also 0 on the left-hand side, and it's just going to be c. So right away, we can start getting our results here. So we see that, in fact, c just equals 0. We can do a little bit of algebra here to solve for a and b. Basically solve for b, because a is already ready to go. A is going to equal -1/2, and that means that in order for a plus b to equal 0 over here, well, a being -1/2, that means b has to be +1/2. All right. Okay, so now we have solved for a, b, and c. So now we can plug those back in, and we can say, okay, well, now we know that the period is going to be equal to, okay, well, this right here, let me highlight it, L over t squared, length over time squared, well, that was gravity, okay? So now we know that what we have is gravity, all right, g, raised to the -1/2 power, okay? And then this expression right here, the next one, in brackets, the length, well, that was the dimension of the length, also uppercase L. And, well, we know that b is +1/2. So here we have L to the +1/2. So notice I've dropped the brackets because I'm moving from the dimensions back over to the actual variables. And then last we have mass, lowercase m for the variable, and to the 0 power. Cool. Okay. Well, that tells us then that the period is equal to, and I'll kind of clean up here because we got, you know, g to the -1/2, L to the +1/2. Well, those are both square roots with g in the denominator. So we just get L over g. Okay. So, strictly speaking, since dimensional analysis didn't tell us anything about the actual initial deflection, all we can say is that the period is equal to some function of initial deflection, potentially, times the square root of L over g. And again, this is because, right, because we didn't know anything about it, we're stuck with that unknown. Now, later on in the course, we'll find out that, in fact, the initial or rather the period is not dependent on the initial deflection, but we can't show that definitively just with dimensional analysis. Regardless, we actually are able to show a pretty conclusive result here, that the period is equal to, or at least proportional to, the square root of the length of the pendulum divided by the gravitational acceleration of the location where the pendulum is located. And most interestingly, it showed that the period of the pendulum, the time it takes the pendulum to swing back and forth, is independent of mass. So that's pretty cool. So we can say, note that, all right, let's just zoom out here. All right. So, okay, no. So put it right here. So say, note dimensional analysis shows T is independent of M. The period is independent of the mass. And that's definitely the most interesting result of this example. All right, and that will conclude this example.